Yeah, sorry, I have to give you the permission, of course. I'm going to give you like this, so.
Nice, thank you.
And I'm going to be with you for a time, but then I have to go out and have meetings and so on. So, but
yes,
yeah,
no problem.
We'll listen to you. So welcome, and you can present yourself and so on. And thank you for being here.
Yes, thank you. Thanks for having us here again. Nice. Okay, so I hope you can you share my see my screen now with the
yes.
share presentation. Yes.
Yes.
Okay. So yeah, welcome everybody to your next lecture with the VLB here. Probably a little introduction of myself. I am Paul Könnecke. I'm a brewmaster here at VLB and a research assistant. I work on different research projects here, also do some lectures, obviously, for our brewmasters we have internally here, and also sometimes for other people around the world. And yeah, it's nice that you have us or have me here today. And yeah, today we will talk a little bit about pasteurization, which is of course a very big topic also in breweries, but of course also in other beverage and food producing industries. And of course we will have today a focus on beer, which is like somehow why we're here all today. And yeah, well, when we come to terms of beer stability, we have, of course, different parts of that, and one of them is the microbiological stability, which is a very, very big point. And especially when we bottle our beers, and if we want to probably also ship it to other countries, but also inside the countries, and this is very connected to the shelf life we can give to our bottled beer. And in terms of microbiological stability, we want to ensure that we have an absence of any critical germ in the beer. So spoiling bacteria are more or less the biggest issue around with yeasts. Could be our culture yeasts, could be also wild yeasts, which could spoil our beer. Then we have the non-biological stability, so which is basically the resistance of our beer against haze formations. We have our flavor stability, which is kind of interfering sometimes if we want to achieve a microbiological stability, especially when we are looking at the pasteurization process. As more intense we pasteurize, as harder it is to achieve a flavor stability sometimes. So our flavor stability, we want just to keep the beer as fresh and as pure in the flavor as it is possible. Of course, the quality of our flavor stability will be reduced from the point we come from our lager tank, and we of course want to ensure that this happens as slow as possible. So especially the formation of stale flavor carbonyls has to be reduced to the absolute minimum. And then in the end, we can also look at the stability in terms of performance stability. So in terms of head retention, as better this is, as slower our foam is, of course, decomposing in our glass. And today we will just have a look at this. So we will just look at the microbiological stability. This is why you pasteurize. And the microbiological stability is dependent on a few things, and the first of all is hygienic work, which is of course including your CIP programs, for example, and that you make sure that this is working well. But also it is everybody who's working in the plant in the end. As better your hygiene in terms of working processes is, as better it is controlled, and as more often you also teach all the people which work in your plant to work hygienically, as better this gets. Of course, everything gets better with the hygienic plant design. So Of course, you did you have some lectures also probably about hygienic design of filling lines, for example? So we basically know a little bit what this means in terms of how water flows can be achieved to be more smooth, for example, and surfaces that you can clean better.
Yeah, we have talked about SIP and so on, but not as maybe not so much the lines yet that we're gonna have this autumn.
Yeah, I think this is also a later thing, but as better your hygienic plant design, especially in filling lanes, is, as easier it is to clean them, and your repetitive cleaning programs will be way more effective. You can also probably reduce the time in that, but in the end, you will have less microbiological biofilms in your filling plant, and this is one very big thing. And then of course you have to have a very tight quality control, and as bigger your volumes get, as more important gets that, because when you miss a point and you probably got an infection somewhere, when you have very big volumes working with, of course you lose a lot of money. So as bigger your brewery gets, as tighter should be your quality control. But of course, your quality control should always be there. Sometimes when you're in a very small place, of course, you don't have a microbiological laboratory for screening that very often. But in bigger facilities, of course, you have to have that just to see what beer spoiling microorganisms probably are in your beer also before pasteurization, and when they appear, and in which amount they appear, because the amount of microorganisms which has spoiled your beer before pasteurization is has a very big influence in how effective your pasteurization is, and also in how intense you have to pasteurize, which will also have an effect on your flavor stability. So this is a very big point. And then in the end, as better we did the first 3 points, as better our hygienic work was, as more hygienic our plant design is, and as tighter our quality control is, as of course less important becomes the microbiological stabilization, because we go into the bottle with a very clean medium. We still have to do that, but when you are doing the first 3 things very good, your pasteurization can be reduced to a minimum, because for example, your initial germ load in the beer of beer spoiling microflora is way lower than if your hygienic work and your hygienic plant design is probably, when this is worse, you will probably have a higher initial germ count, and then your microbiological stabilization has to be more intense. It is always the goal of a brewer to achieve perfection, or next to perfection, to the first 3 points, to be as less intense as you want in the 4th point. And luckily, brewers, we have a good medium to work with when it comes to pasteurization, because beer is self-protecting itself against a lot of microorganisms, mainly through the 4 points of that it is oxygen-free after fermentation. We have alcohol in our beverage, which is high enough to inhibit the growth of a lot of bacteria, and especially bacteria. We have a low nutrient availability if you leave the alcohol besides, and we have a comparably low pH. And those four facts are inhibiting the growth of a lot of bacteria, also, which is very important, mostly all pathogenic bacteria. So everything which really makes us sick is not really able to grow in beer. But there are some microorganisms which are able to grow in beer, and those can cause some serious issues, mostly in terms of flavor stability, in terms of a flavor change, going from a little bit more of acidity from lactic acid to that your beer is tasting like your toilet, and this is not what you want to have. And this is also, of course, ruining your customer's reputation. And then you can also have some yeasts which will cause some very serious trouble in terms of post-fermentation. For example, Saccharomyces diastaticus is able to let some amylases into your beer and also break down some dextrins, which are probably in there, and then there will happen a fermentation in your bottle after you filled that, if you didn't do a pasteurization. And then probably your bottles are way too high carbonized, and sometimes this can even lead to explosion of the bottle. So there can be some serious issues. Luckily, nothing which is really making people sick, but we have some bacteria which can grow under those conditions. Lactobacillus, Pediococcus, Megasphaera pectinatus, and yeasts are the most common ones we are looking at. And against those, we want to stabilize. And we can stabilize our beer in a variety of different ways. When we look at the microbiological preservation of beer, we can basically do this before filling or after filling. And before filling, of course, there's always the issue that you then have this point of filling the beer into your bottle, which is also a point, can be a point of contamination. So when you do a microbiological preservation of beer before filling, you have to assure that your filling process is as clean as possible. And the most common way of microbiological stabilization before filling is the flash pasteurization. We will come to that in detail later, so I will just go a little bit over this overview now. We can do a sterile filtration before this. Also, we will come to this in the very end of our hours we have here, but this always, of course, has to happen after a proper filtration of your beer. You can't just sterilize your beer by filtration when it's not properly filtered before, but we will come to that a little bit later. And then, of course, we can have some chemical methods. I will not go into those chemical methods in detail because this lecture is about pasteurization, but probably, did you hear about Valcurin, for example? Nobody? Okay. This is, yeah,
excuse me, could you repeat what you said? What was called?
Valcurin. It's a brand name, basically. It's a chemical which is induced into the beer right before filling, and then starts to react in a way which harms everything which is living next to it. And this Valcurin is then reacting until it's done, and when it's done, we have just methanol and some carbon dioxide left. This is it's working. So if your initial germ count in your beer is low enough, you can just dose this, and then in the end, your bottles, they are just toxic for half an hour to 2 hours when the beer is filled, and then everything is reacted, and the amounts of methanol in there are not toxic. So this is something which is done sometimes. The regulations for this are country specific. Valcurin and other methods are allowed in the EU, but for different beverages in different countries. So for example, in Germany, you can't use Valcurin for beer, but you can use it for beer mixed drinks. For example, beer with lemonade, you can use that. It's more a thing in wine production and also in juice filling. But I just wanted to give you also this in a little overview, and I will not talk about this later on, so I just wanted to mention this. There are also, of course, some other chemicals you can use. Most of the times, those are not used in beer just because the pasteurization is very effective in beer, as we will see later. And then we can, of course, achieve stabilization after filling, which is mainly done when you have a big brew through tunnel pasteur. Also, sometimes if you have a small brewery, you have chamber pasteurs, pasteurizers, which basically do the same thing, just in smaller amounts and in batch-wise and not in a dynamic way. And then we can do hot filling. Hot filling is something which is also not really recommendable for beer, but it is a method which is theoretically possible and also has been done. I think sometimes it's just not that suiting for our medium, but I also wanted to mention it here. So you see there's not only methods about thermal stabilizations. You can also try to filter until your medium is sterilized, for example. But pasteurization is thermal stabilization. And to understand a little bit better what we want to achieve, we have to understand a little bit better how temperature is affecting our microorganisms. And the temperature, when we look at an increasing temperature curve, of course, when it's very cold, our microorganisms don't grow. That's the same thing as you achieve when you put your stuff in the refrigerator. Nothing grows in there because everything's frozen. And as warmer we get, we will at a certain point, and this is microorganism specific, will reach the minimum growth temperature. The microorganisms will not like it there, but they can grow very slowly, but they can. And as more the temperature is increasing, the cell growth is going faster until we reach the optimal growth temperature. For yeasts, that's also media specific, but around 28 to 30 degrees, depending a little bit on the type. And then we, when go higher with temperature, we will see an increasing a decreasing growth rate due to an increased cell death while we still have a growth rate, until we reach the lethal temperature where very fastly our microorganisms will die, and you will see no growth anymore. And this is mainly due to 3 points of protein denaturation, the denaturation of nucleic acids, and the damage of the cell membrane. So the very inner parts of the cells are just destroyed. Our proteins fall out of structure, our nucleic acid is falling out of structure, and the cell membrane gets loose, and there's an osmotic pressure difference, which is then not there anymore. And yeah, our cells dilute and they're dead. And all of this is dependent on the condition and the type of the microorganisms and the medium. So, for example, lactobacillus, so lactic bacteria have another lethal temperature than yeasts, for example. And also our yeast will endure temperature in another way in a fruit juice than in our beer. And we have to know this for really calculating how much energy and how much temperature we have to apply to our medium for achieving microbiological stability through pasteurization. And so if you look at the influencing factors of thermal stabilization, of course, I said this, we have to see that every species and the condition of the microorganism is influencing that. So we can't tell this just as general, for example, for all beer exporting microorganisms. And then the amount of germs is a thing which is very, very important when you look at pasteurization. We will also come to that in detail probably in the next over next sheet. And the temperature, we saw this, yeah, we have to achieve a certain temperature for cell death, and then the exposure time. So at a certain temperature, which is probably lethal, but very, very on the edge of being lethal, we will take way more time for killing the biggest amount of microorganisms. And when we go more up with the temperature, then we will need way less time. This is basically also the difference between pasteurization in a tunnel pasteurizer and the flash pasteurization, where the flash pasteurization is happening at way higher temperatures for way lesser exposure times. Then, of course, it's media specific, and there are a few things which have an effect on the heat resistance of microorganisms. First of all, it's the water activity. Did you hear something about water activity? Probably in terms of, I don't know, malting. There's also, for example, the Maillard reaction, the browning and flavor reaction in malt is also dependent on the water activity. And the water activity is basically defined as the water vapor partial pressure in the food, so also in the beer, in comparison to the pure water saturation water pressure, so vapor pressure. So the water activity of water is 1. And as less water we have in our medium, as lower gets the water activity. And when there is not that much water around, for example, in I don't know, in a cracker or something, then the microorganisms in there, they're not active, but they're also way more resistant to heat application. Also, their enzymes, which is one of the reasons why they're more resistant, are way more resistant to heat application. For example, probably you also heard that in terms of malting. This is why you dry out the kernels before you go up with the temperatures and kilning, because then you have a lesser water activity and your enzymes are way more stable against denaturation. Yeah, we measure the free availability of water. Of course, we have to have a certain water activity for growth, but as lower this is more heat resistance, especially some microorganisms are. And this lack of water slows down cell growth, as I said. The exceptions are, of course, xerophilic microorganisms. There are some yeasts which are xerophilic. It's not the yeasts we use in the brewery, but there are some yeasts which can grow marmalade, which has a very, very low water activity. And every yeast is somehow able to stand, for example, higher amounts of sugars than other microorganisms normally are. So all yeasts are not xerophilic, but they are more resistant to higher sugar amounts, for example, so to also lesser water activities. The pH value is very important. So when we increase, so as bigger the difference from the pH optimum for the microorganism is, as more heat sensitive it is also. And of course, we have different pH optimums for yeast and bacteria, and not all bacteria have the pH optimum of 7. That's just a little example. But we can see that with a decreasing pH, the killing effect in our thermal pasteurization, in our thermal stabilization increases. And which is also good for us, because beer, of course, has a way lower pH than 7. So our thermal pasteurization, is way more effective, and we will have to apply temperatures for a lesser amount of time than in water, for example, which with a pH of 7. And then we have those things like sugar, lipid concentration, protein concentration. All of those, as higher our sugar and starch concentration is, as more lipids we have in our medium, and as more proteins we have in our medium, as lesser effective our thermal pasteurization is, because all those can increase the heat resistance of microorganisms. Sometimes because of the formation of protective colloids, also sometimes just because of, so for example, the sugar, when you have a bigger amount of sugar soluted in your medium, the water activity is lower because there's a lot of water bound to sugar, which is not counting to the available water, for example. Proteins can form like little bubbles around microorganisms and protect them from heat application. Lipids can sometimes do the same. And of course, microorganisms also try to protect themselves. So exopolymeric substances, like you can find them a lot in biofilms, for example. When you're, I don't know, in your filling lane, for example, when you have this place where nobody cleans, never, and then you have this biofilm, this muddy thing under there. The microorganisms in there, they produce a lot of substances which protect them against heat and other things which can come from outside and kill them. Of course, the formation of permanent forms makes microorganisms more heat resistant. Spores, we're talking mostly about spores here. And yeah, so after we know all this, what we want to achieve by pasteurizing our beer. And the first aim is the modification. So basically the germ reduction and the reduction of vitality of our products boiling microorganisms. And this is by definition not a sterilization. If we sterilize something, we kill everything in it, and we can't achieve this with a pasteurization. That's just not possible. But we can reduce the amount of microorganisms to a point where they don't matter, or probably where they are still in there, but they're not able to grow anymore. And this stands against a few other things. For example, or basically the main ones are low influence on our sensory properties and low energy consumption, which is a classic conflict of goals, because as more intense our pasteurization is, as better is our modification, but as bigger also our influence on our sensory properties will get. And of course, we will consume more energy when we pasteurize longer and or at higher temperatures. And if we look at the requirements, if we want to achieve both more or less, one of the main things we have to achieve by filling is a low oxygen content, because as higher our oxygen content is, as higher is our oxidation, our aging process. And probably from when you had some lectures about sensory evaluation of beer, for example, you probably heard about forced aging. So you put a beer to warm conditions, then to cold conditions, then to warm conditions again. This is also, of course, used for seeing whether the beer is microbiological stable in terms of turbid formation, but also you can see, you can somehow foresee the aging process in terms of flavor stability. And this should give you a hint that heat is always enhancing this aging process. So if we, for example, fill our product with a high oxygen content, if our filler is old, for example, or when we fill cans, our bubble breaker is not doing his job, or our hot water injection for our bottles is not working well, and we have a higher oxygen load, higher total oxygen content in our containers, a following tunnel pasteurizer will just age your beer in half an hour. And this is something we really don't want to have. So your influence on sensory properties is highly influenced by the oxygen load you get while you are filling. And so this, for example, is also something which you don't have when you have a flash pasteurization and pasteurize before filling. But then, of course, you have to have very hygienic filling for not bringing some contaminations in that filling process. And then we will have to look at the headspace of our bottles, for example, because our fluid in there will not really expand, but what wants to expand is the carbon dioxide, which is soluted in our beer. So the pressure in our bottle will increase, and the only place where this carbon dioxide can go is the air or carbon dioxide or volume about your fluid. So we have to have some headspace just not to explode your bottles in a tunnel pasteurizer. And there you have a little bit of a rule for that. So for each temperature difference of 10 Kelvin, you want to have 0.6% of container volume for headspace. So when you do a little calculation for 520 milliliters and a temperature difference of 50 Kelvin, you more or less want to have 3% of your volume in your bottle to be the headspace for preventing explosions through pressure, through increased pressure while pasteurization. And in the end, we want that no pathogen microorganisms survive, which is really easy in beer, because they don't grow there anywhere. So probably you don't have a lot of them in your beer initially. And even if you don't pasteurize it, your beer will not make you sick. This is also why beer is so successful over thousands of years, because it makes the water you drink way less dangerous in terms of pathogenic microorganisms. So when we look at the intensity of our pasteurization, it is of course dependent on our product matrix. For example, when you have a wheat beer, German Hefeweizen, for example, the protein load in that is just way higher. And we recently learned that the amount of proteins in our medium can also increase the heat resistance of our microorganisms. So our product matrix basically defines our growth conditions, and those are defined through the availability of nutrients. What atmosphere do we have in there? Is there oxygen available? Is there no oxygen available? That's basically the question. What is our pH value of our beverage, of our medium? And are there growth inhibitors in there, for example, alcohol? And in the end, are there protective substances which can protect our microorganisms against an application of heat? And this all, of course, is then influencing your decision, but there is also this big thing of the required shelf life. And probably when some of you are working in big breweries, so for example in Germany, big breweries are sometimes just forced to give a certain shelf life by the supermarkets. So when a supermarket says that you want to be in that supermarket listed, and they say, yeah, well, you give half a year of shelf life, but we want to give you a year. Then if you want to be listed there, sometimes you have to do things, and then probably your pasteurization has to be more intense, or your filtration and your sterilization has to be more intense before pasteurization for achieving a better microbiological stability. And of course, so the shelf life is something, as long as this has to be, of course, the intensity of pasteurization has to go up. The sensitivity to off flavors is also a big thing. Of course, beers can be very different in the flavors they bring, and those flavors are more or less sensitive to heat application. So we also have to be aware of that. And on the other hand, we have our operational hygiene, which is in the end leading to an initial germ count. And this initial germ count is then influencing how intense we have to pasteurize. The growth conditions so limit the potential microflora, and together with the initial germ count, those determine the required intensity. And the initial germ count is something we have to look at now. And for this, we have to go a little bit into math, because we have to get familiar with a few things like the d-value, which is the decimal reduction time. So basically the amount of time it takes to kill 90% of the microorganisms at a certain temperature, which is of course influenced by the temperature and the water activity and the pH value, but it is organism specific and media specific. So the d-value for yeast is not the same in water and in beer, and the d-value for a pediococcus is not the same in beer than it is for yeast. So those d-values just differ for every microorganisms in every medium. So just to give you a little example here, when we have this little chart here, you see the survival curve, and this survival curve is just a line because the y-axis, so no, the why not? Oh, it's y-axis. The y-axis is pointed out logarithmically. So the killing curve is also an exponential. But if you point out this logarithmically, of course, you will get a ln. And you can define the d-value, the decimal reduction time, as the holding time divided through the amounts of amount of microorganisms which is there initially and after that certain time, and about that you get this decimal reduction time. Just you have to find this out by experiments every time for a new medium and a new microorganisms. Of course, this has been done for beer for a lot of microorganisms, so you don't have to calculate that. You can just look that up. And yeah, just to give you a little example, so the decimal reduction time here, as you can see, is just when we come from like, what is this, 10,000 to 1,000 germs. And what time do we need to achieve this at the temperature 80 degrees? So what can we expect? And we have the temperature of 60 degrees. Of course, we will have a lower or a higher d-value, because we need more time to reduce the same amount of germs. And from this d-value, you can come to the z-value, which is defined as the temperature that is required to reduce the decimal reduction time by the factor of 10. So basically, or in other words, reducing the decimal reduction time by 90%. And this is this value is pretty important when you want to calculate pasteurizing units. But this Z value is in fact included in the terms I will give you later. But this is relating to the resistance of a microorganism to differing temperatures. And when you know those values, you can calculate the thermal process equivalency. So for example, when I have 64 degrees in my tunnel pasteurizer for half an hour, how much time do I need in my flash pasteurizer at 72 degrees? And to calculate this, you always have to look at the microorganism, because also the Z value, of course, because the D value is microorganism specific, the Z value is as well, and it is also media specific. Bacteria spores normally, for example, have a Z value of 10. So if you increase the temperature of pasteurization by 10 degrees, you will achieve a 90% better or 90% lower decimal reduction time. So the bacteria spores, the same amount of bacteria spores will be killed in 1/10 of the time that it is killed by as in the initial temperature. And the problem with the Z value is that it's only valid for narrow temperature ranges. So you can't really compare 50 degrees to 90 or 40 degrees to 100. That's not really possible. But you can compare, for example, 60 to 67 degrees. And just to also give you a chart to that, when we look at the Z values. So in the y-axis here, you see the decimal reduction time with a factor which is then in the end defining the total lethality. So the total lethality is basically the accumulation of all lethal factors, and the decimal reduction time is, by its definition, about temperature, one of them. And so the Z value, if you want to put it into your formulation, it looks like that. So for example, when we have a temperature increase of 7 degrees, and it's just an example, this example is just for yeast, you will see that you will have a reduction of 90%. But all this, it's basically not able to calculate that. You really have to find that out by experiment. So we will have a little bit more now of another thing, which is the probability of sterility, and this will in the end then lead us to the pasteurization units. So basically all this math was done before, all those experiments were done before, and in the end you can just look up pasteurization units in the end for your microorganisms. So the probability of sterility, which is probably when you saw the formulation for pasteurization units, is looking very similar, because in the end the pasteurization units give you an overview about the probability of sterility. And for an example, when we have an initial germ count and 0 for like with what's that, like 100 million cells per milliliter, and we have a decimal reduction time for that specific microorganisms in that medium at 121 degrees of 2 minutes. And we hold this temperature for 60 minutes. How probable is it that our medium is sterile? Turns out not that probable. That's that's due to, and probably as also in this formulation you see this very good, the initial germ count is high. So it takes a lot of time to reduce that initial germ count to 0. So as lesser your initial germ count is in your beer, as better your probability of sterility is, and as shorter and less intense your thermal pasteurization can be. The difficulties about that, as I also mentioned, is that all of those things are very, they're just media specific and microorganism specific. So so yeast will have another that value than a lactobacillum, for example. And you have to accumulate a lot of data to really find out what is the probability of sterility at certain temperatures. And for this, we have the Pasteur units of beers, which somehow give you a not very exact, but most of the time exact enough overview about how hot for what amount of time you have to you have to have your beer. And this is why we use it in the beverage industry. It's basically to measure the thermal treatment of products, and they describe the cumulative lethal value. And this was first this cumulative lethal value has a lot of to do with the Z factor, which we saw before. And this was observed first by Röseke, which is one of the founders of VLB. He just saw that between 60 and 90 degrees, the temperature increase of 7 degrees increases the killing of different germs by a factor of 10 under otherwise identical conditions. Those 7 degrees are a little bit higher than for all of those microorganisms necessary. So, for example, for the Z value for yeast in beer is not it's not 7 degrees, it is 6.95 degrees. But those 7 degrees in the end cover everything we want to have for beer. And so this increase means that our decimal reduction time, as we learned, is reduced by 90%, which means that the new temperature is 10 times more effective in killing our microorganisms. That's basically what he found out. And if you put this now into the formulation of the probability of sterility, you really don't have to learn that just for giving you a little overview how we come to that in the end. We can formulate this also as the effectiveness or the lethality value. And in the end, with the time increase, we have an increasing effectiveness. So this effectiveness is also time dependent, as you can see in this formulation. And in the end, we use in the brewing industry the base D0 means that at 60 degrees, we know that yeasts and other beer spoiling microorganisms are effectively killed. And when you hold a temperature of 60 degrees for 1 minute, we get 1 pasteurizing unit, 1 Pasteur unit. And if you now put this to the space of 60 degrees, and if you know that this 10 to the potence of 1/7 is not the 10 to the potence of 1/7, so but it is 10 to the potence of 1 through 6.95, you come to this 1.393. And in the end, this is the definition of our Pasteur units we need and how we can calculate them. So we know that under 60 degrees, we don't count Pasteur units, and we say, okay, our killing is not effective enough for really saying that we can reduce the initial germ count by the amount we want to have. But when we come to those 60 degrees, we say, okay, we can now do this. So, for example, when we say this is the temperature of the thermal treatment, and this is 62 degrees, we in the end get 1.393 potenced by 3. And this leads to, as example, when we have a temperature of 72 degrees for 0.5 minutes, and we hold this temperature for half a minute, we get 26.7 pasteurizing units. This is a lot of stuff now. Probably I will do a little stop here that if you have some questions at that point, I would try to answer them.
I mean, this is all very theoretical, but I guess there are experiments done to sort of test this all out. How different, like if you're looking at a beer, how different beers have different, like, can you say for a Pilsner has this kind of a number, or if you have an IPA, it has that kind of a number. I mean, how different are the media's effect on these calculations? Would you actually have to test it out on every kind of beer or on your recipe?
Yeah, basically somehow yes. So this calculation of the Pasteur units does not mean, it's not really including the different medias. This is basically was done with a filtered Pilsner beer, I think. So of course you have to change that, but in you don't change, in this case, the formulation. You just say, okay, I will apply more pasteurizing units. So a wheat beer has to be pasteurized at way more pasteurizing units, for example, than a Pilsner beer. Pilsner beer, I will give you some charts for that, of course, what amount of pasteurizing units you have to apply with different beer styles. But the comparison between a wheat beer and a Pilsner beer is quite big. So I think for a wheat beer, you need like sometimes around 500 pasteurizing units, just because you also want to inactivate all the yeast which is in there, which is not filtered away. So you have a very, very high initial germ count. And for a Pilsner beer, you can, sometimes 15 pasteurizing units are enough. So there's a very big difference in what you have to apply, of course.
But say you have, so I understand there's a difference between like a Weizbier and a Pilsner beer because you have a higher microbial count. But if you just like, I'm just thinking about the basic beer recipe of let's say a 4.5 ABV and I don't know, it'll be a different kind of a hop content, or I don't know, just like how specific do you have to be in calculating out the effect with the medium?
You basically can't calculate that out because it's
You
specific for every medium. What you do in your brewery is you probably, for example, when you have a new recipe, you and you know, okay, this is somehow comparable to this one, probably from the amount of hops we had in there, for example, from the alcohol content, and then you apply probably first the same pasteurizing units, and you have a microbiological screening. Of course, this has to be part of your quality control, and then you see whether you are able to reduce the microorganisms to a point where they don't grow after pasteurization. Basically, you have to find this out for every beer in your brewery, but there are some ranges where you know you are quite safe when you do that. Yeah, but in the end, you can't really you can't really say that. This is why I went through all those charts somehow. Like, it's good for you to see that, but basically, everything you know, so everything you need is this one, because everybody's counting with those pasteurizing units, and this factor here, this 1.393, this is used for beer. And of course, for different types of beers, it's more or less correct. And when you go to juice, for example, you have another factor, and you also have another base for that factor. So the base is not 60 degrees for 1 minute, it's 80 degrees for 1 minute. And then you say pasteurizing units for juice, which are not the same pasteurizing units as for beer. But you mentioned that correctly. It's very media specific, and you have to find that out somehow. But yeah.
When you do the experiments to find it out, I mean, there aren't that many. There isn't that, usually there's not that much, well, except for in a Weizbier maybe. But so do you spike your beer and do the experiment? Spike it with microbiology somehow to actually see the death by pasteurization?
This is what we do here at VLB sometimes when we do this kind of experiments. You don't do this in breweries just because this is the worst case you do. You bring in beer spoiling microorganisms in a little container and do some experiments in your brewery. You don't do that. So there are a lot of recommendations of how you should pasteurize which type of beer, more or less. And normally those work. But they just work when your working hygiene and your hygienic plant design are good enough to have a low initial germ count. So we just know at those temperatures, microorganisms are killed. But when there are so many in the medium, your pasteurization will not get all of them.
Yeah.
So this is basically what is your task as a brewer is always trying to pasteurize beer with the lowest initial germ count that's possible.
Yeah. Okay.
And as worse your hygiene is, as more you have to pasteurize. But there's no, you can't really say this specifically, and you can't really calculate this for all your beers. The amount of experiments would be too much.
Okay, thanks.
All right. Then we will proceed a little bit more until we do a little break. So just to give you a little bit of an example for how to calculate your pasteurizing units, your Pasteur units. When you use the temperatures 60 degrees, you will in the end have this 1.393 to the potence of 0, which is 1 always. So your pasteurizing units are equivalent to the time you apply them. So 20 pasteurizing units equal 20 minutes in a pasteurizer for beer at 60 degrees. This is a normal temperature, for example, for a tunnel pasteurizer. Well, not 60, but probably 62, 63 degrees, dependent a little bit on your technology. And for a flash pasteurization, you see you need way lesser time to achieve the same amount of pasteurizing units because now the temperature is way higher. So the potence for our factor is 12. And this also probably leads to the knowledge that a time increase is always not as effective as a temperature increase when it comes to the effectiveness of pasteurization. So you can achieve the same amount of Pasteur units in a way lesser time when you just go up with the temperatures by 12 degrees. And also, given how tunnel pasteurizers and how flash pasteurizers work, and we will also come to that, of course, it's of course way more effective in terms of energy consumption. When we look at Pasteur units for fruit juice, as I also mentioned just before, we have a different base for that. We have a base of 80 degrees for 1 minute is 1 Pasteur unit, and the overall Z factor for the amount of spoiling microorganisms which can be there is around 8. So with this knowledge, we come to another formulation, which is then a formulation for the Pasteur units for fruit juice. And you see this factor is a little bit lower due to the higher Z factor. In the end, but the calculation just stays the same. So for example, when we apply 95 degrees for 2 minutes, we put this in our therm, we get like 63.3 pasteurizing units, which I would have to look this up whether this is okay for juice. I'm not really a juice producer, but with juice, just imagine that there's so much more sugar in there and there's no alcohol. So there's a lot of other microorganisms which feel comfortable in this type of media. So those microorganisms are probably also, and as you can see in this term, they are more resistant to heat application. So your heat application has to be higher for guaranteeing a safe product. And probably what you can also see here, what I also mentioned before, temperature increase is more effective than time extension. And on the other hand, time extension has a bigger effect on your flavor stability. So a flash pasteurization is always more favorable in terms of flavor stability. It's just not as safe as a tunnel pasteurizer is because we don't pasteurize the closed containers. And probably for your, to give you a little bit of an overview for the question you had before, necessary pasteurization units for different types of medias. You see when you have a beer, and this is a filtered beer, we really have to say that it's filtered. then your pasteurization units don't have to be higher than 15 to 25, dependent on the hygiene you're able to achieve in your brewery, of course. When we look at malt beer, it's you see malt beer is something which is not that specific. So sometimes there's alcohol in it, sometimes there's no alcohol in it. What amount of sugar is in there? How is the pH adjusted? Everything is influencing that. But when you have a product which is basically giving microorganisms a lot of sugar, you will have to apply a lot of pasteurization units to that medium to be safe. So malt beer is pasteurized for example, way higher pasteurizing units. Of course, beer mixed drinks, everything in the end which does not contain that much of alcohol or is filtered that clean and has for this a very low initial germ count requires higher pasteurization units. And as you see, I was wrong. Those 500 pasteurization units is for alcohol-free beverages. Wheat beer is between 100 and 120. So sorry for that mistake. Didn't have this in my head. And yeah, well, when you look at fruit juice, we already have those 80 degrees, and we still have to have this big amount of pasteurization units for really being safe. So this is something you really have to know if you're probably also producing sometimes juice in your, I don't know, I worked in little craft beer breweries, and then we were sometimes just producing apple juice for a day or two. And of course you have to adjust your pasteurizer to that for really being safe. So just keep this in mind. Also, what gives you a little bit of an overview is this table here. It looks a little bit complicated in the beginning, but in the end, it's pretty simple. You can just see, okay, I have this and this temperature. When I want to bring this amount of pasteurization units, how much has my exposure time to be for a certain beverage or for a certain microorganism to really achieve a more or less complete killing of all my germs. So for example, when we come from here, 68 degrees, we can just go up, sorry for my poor drawing skills. And we want to have like what we have here, that's a tenth. So that's 30 pasteurizing units here. That's the 30. Also, this is a logarithmic logarithmic table, so don't be confused by that numbers. And so we want to have like 30 pasteurizing units at 68 degrees. Our exposure time has to be 2 minutes. So not that much, because temperature increase is always more effective than time increase, as you can also see in this table. And yeah, so where we landed here is somehow like the accumulation of everything we want to kill in our beer. So this is why this field, this blue field here is beer. And you see, you have to go, you have to have the same temperature. You have to have more pasteurization units, for example, for an alcohol-free beer or for wheat beer. And of course, way higher temperatures for malt beer. And just it's basically the same as in the table before, but you can just, you know, okay, I pasteurized my beer with in this amount of time with this temperatures. How much pasteurizing units more or less did I achieve without calculating that? So probably this can also help you a little bit. And just to give you also a little bit of an idea how those different D values matter. So when you look at Saccharomyces diastaticus, which is one of our really main beer spoiling microorganisms, which we don't want to have because it can ferment dextrins, which other yeasts can't. You see that the D values are just as higher you go with these temperatures, as way more effective is the killing in terms also of the decimal reduction. And those D values, of course, are different to the D values of Lactobacillus brevis, which has another sustainability against heat, a way better stability against heat. So to achieve a complete killing for Lactobacillus brevis, for example, at a cell concentration of 1 million coliform units per milliliter, there are over 140 Pasteur units necessary, which is something. So when you really have a contamination before, even though you can't taste it probably, which is unlikely, but sometimes it happens, and you have this high initial germ count, your normal pasteurization won't really work. And just to show you how important it is to go to your pasteurization with a very low initial germ count, because this decimal reduction is just when, and the problem is microorganisms grow exponentially. So when you give them enough time, even if they didn't influence your media in types of flavor, they are just so many that at a certain point, your normal pasteurization is not working well anymore, because your pasteurization units are set to a medium with a way lower initial germ count, which is also an example for how important your quality screenings are, because your quality screenings will show you this, hopefully. But in the end, they can say, okay, we have a very, very big load of microorganisms in there. Okay, the taste is okay. We can probably still fill this, but we have to go up with the pasteurization units for this specific tank. And this is something you really have to have in mind, that your initial germ count is just a very, very important thing. Also, of course, you can bring up the Z values of Saccharomyces yeasts to the D values, and then you see if you have this, for example, for Saccharomyces yeast, this looks linear. It is not really linear. The problem is the Z values can differ in tiny amounts, but those tiny amounts, due to the due to how we calculate in the end the Pasteur units, can lead also to a incomplete pasteurization when you go to other temperature levels. So the temperature difference from 60 to 72 degrees, there we have this basically 6.95 degrees Celsius. From 72 to 84, the Z values may differ. And this is something you just can't find out by experiments. For example, for Pediococcus damnosus, there have been done those experiments for different temperature ranges, and they were looking at, okay, what is in the end the Z value, which allows us to calculate the amount of pasteurization we have to apply. And you can see between 50 and 60 degrees and between 60 and 72 degrees, the Z values differ, and also between 60 and 72 and 84, the Z values differ, and the Z value goes down, which in this case is a good thing. For Lactobacillus brevis, it's another thing, and I said before that when we calculate pasteurizing units for our beer, we say, okay, we need a Z value of around 7. Because normally all those microorganisms at the temperatures we apply or we put into the medium, they stay under this 7 minutes. And so we, in fact, when we calculate with those 7 minutes of Z value, we are safe. But for certain microorganisms, sometimes this is a little bit different. For example, Lactobacillus brevis is at 7 or probably a little bit higher. Those experiments were of course, they also have a little mistake. But as you can see, when you pasteurize a beer which is spoiled by a lot of Lactobacillus brevis contaminants, and you flash pasteurize this in this temperature range, and you probably narrow in your calculation about how many pasteurizing units you need, you will probably not kill all of them, and then you have a lactobacillus infection after your flash pasteurization. And this is something you really have to know. So let's just come after this very, very theoretical part to a little summary of what we have talked about. So Saccharomyces yeasts are easier to inactivate than Lactobacilli or Pediococcus, but the current pasteurization unit calculation for 60 to 70 degrees are correct. For yeast, a certain security is calculated. Also, our lactobacillus, our lactic bacteria are covered in this temperature range by the normal calculation of our pasteurization units. Z values, for example, for Lactobacillus brevis are sometimes higher than 6.94 for temperatures higher than 72 degrees. This means that our real inactivation rate is sometimes lower as calculated, and we have to know this. For example, when your quality control tells you, okay, we have this specific microorganism, we have a Lactobacillus brevis infection, probably just go a little bit higher with your pasteurization units as you normally do, just to be sure. Flash pasteurization at low pasteurizing units, for the example that was given, at higher temperatures and at a high contamination rate can lead to an insufficient pasteurization because the Z values differ over the different temperature ranges, and the thermal treatment still increases significantly the shelf life and protects against spoilage. So even if you don't kill them all, which you of course can't do in a pasteurization, you will kill a lot of them. Just really be sure that when you have a high contamination rate, probably go higher with your Qs. But in the end, a complete safety is not given, especially at high cell concentration and calculations at high temperatures. So normally pasteurization works, but sometimes it's very narrow whether you really achieve the time at a certain temperatures when you have a high initial germ count. And this is just what I wanted to point out with also this amount of calculations and data I brought you from some experience. We are now, of course, not in the half of the time, but we are most in the half of our presentation. The other part of the presentation will give you a better overview about how pasteurization methods work, how also the technology behind this is built, and what are probably some things you have to know about that. And I would say we do a little bit of a 5-minute break now after this 1 hour of a lot of theoretical stuff. So yeah, let's say we meet again at 10:15 for the second part of the presentation. But if you have some questions now for this part, and just feel free to put them now. Otherwise, you can also, of course, write them in the chat. I will, if there is a chat, is there a chat in Zoom? I think so. Yeah. And I will have a look at this at the end of the presentation. But if you have something now, just say it now, and then we will go to our break. Okay, nice. Then see you in 6 minutes. I can. Oh, nice. Okay, so let's come to the second part of our lecture here. And first, probably let's have a look at the process for the thermal treatment of beer, which is basically what we want to look now in detail. And when we look at the thermal treatment of beer, we can have, as I also mentioned, flash pasteurization, tunnel pasteurization, chamber pasteurization, and hot filling. Those are the thermal treatments which are applied with a very high amount of things happening at flash pasteurization and tunnel pasteurization. Chamber pasteurs are normally a thing of smaller breweries, where it's just not suitable to have a tunnel pasteurizer because those machines are very big, very cost intensive, and have to run very dynamically over a long time to not be energetically a complete catastrophe. So normally in small breweries, you also find chamber pasteurizers, and hot filling is something which is not that easy with beer, just because you fill at temperatures which pasteurize. So you fill a pasteurized medium into a container, which is then also heated up, and this, like, the medium is pasteurizing the container from the inside. But if any one of you just filled beer at certain higher temperatures with a filler, he knows that over foaming can be a problem just 5 degrees over the normal filling temperature. Just when you reach the saturation pressure and go above this, carbon dioxide tends to come out of our fluid quite fast, and this happens faster if your medium is warmer, which is why hot filling is not a thing at the moment at most of the breweries, just because this amount of time between coming from the filler and then then close the container is too long for not having this over foaming. This is probably a little bit changed due to new technologies. For example, the Dynafilter technology from Kronos, where you do a vacuum filling and the container is closed in the filling organ, which could lead to probably a comeback of the hot filling. But normally what we can see in breweries is a flash pasteurization or a tunnel pasteurizer. And I want to start with tunnel pasteurizers since they are very common. They're also there for quite a long time. They changed a little bit over time. Basically, how do they work? So we have a slow transport of the containers through the pasteurizer, and while this transport, the containers are heated up slowly and in different steps. And as more modern those pasteurizers get, as more small and more steps you have. In the end, you want to achieve a certain temperature in the container in the middle of the tunnel pasteurizer and hold this temperature for a certain time. After the pasteurization, so after this middle transport, the container is then cooled back to a temperature which is suitable for packaging, for example, also for suitable for packaging is mostly the thing, and also for those slow amounts of heat differences which are applied are basically so that it's good in terms of recuperative energy use, but also in terms of not stressing the glass, for example, too much, that we can, if we have some thermal little cracks in them, we will grow them and probably the bottles are exploding in the tunnel pasteurizer, which they are sometimes do. And the throughput time for glass bottles, for example, through tunnel pasteurizers are between 40 and 60 minutes. With cans, it's more or less the same, but not every can is able to go through a tunnel pasteurizer. For example, highly carbonated drinks, when you come up to those like 6 or 7 grams of carbon dioxide per liter and you fill this in a can, it's very likely that a lot of cans get lost in the tunnel pasteurizer in terms of they just unfold the lid and then they explode, because cans are not that stable against inner pressure. And the material of what a tunnel pasteurizer is built of is most of the time stainless steel nowadays. Just to give you a little look of what how this is working, in the end we just have drops of water coming from the top and going over our bottles. Normally modern pasteurizers have 2 floors when they are big enough, or when it's required to pasteurize a lot of bottles. Those bottles are just over each other, and this flow is applied through different applications in both of the levels. And in the end, we have hot water basins under our pasteurization part, and not that hot water basins as far as you get away from that pasteurization part under the bottles, from where those heat applications, those water applications feed it. And of course, you work with heat exchangers not only to heat up the water basins in the middle, but also, and this is how those tunnel pasteurizers basically work, is that you use the bottles as an heat exchanger for your different levels where you heat up or cool down. So it's probably best to see this in that picture, this bassin here is right behind our pasteurization area, which is here. So this orange thing is our pasteurization area, where the bottles are held at the pasteurization temperature, so where they reach 60 degrees or a little bit above, and are just brought through this zone in the time you want to have for your certain product, which then defines pasteurization units. And after that, you want to cool those bottles down, and you want to do this with water which does not have 10 degrees, but is like a little bit lower than the pasteurization temperature. So what happens here is that the water which is sprayed over those bottles, it's coming from the last preheating bassin here, going through here, all over there, and is applied to those bottles. And this water of 47.3 degrees in this example is then through the hotter bottles, because those bottles have around 60 degrees when they come from this zone, is heated up to 49 degrees. And I'm sorry for my bad signing here. And this 49 degrees water is then used for the last preheating step before we have the final pasteurization area. And this is happening also from this area to this area, and from this area to this area. So what we want to achieve in a tunnel pasteurizer is as less heat application from outside as we can, and this is achieved by that we connect zones which have comparable temperatures and use the bottles which go in there as a heat exchanger. So the water is flowing over those bottles, is heating up or cooling down, and the water is then catch up in those basins and pumped to the point where its temperature is good at this moment, which is most of the time the comparable side on the other side before or after the pasteurization area. So our bottles are infeeded here and are then slowly heated up through the different zones until they reach the pasteurization area. And from this point here, we count the pasteurization units until we reach this area where they are cooled down. And from this point here, we don't count the pasteurization units anymore, because we will go under 60 degrees with our bottles. And the only point where heat from external heat is applied is for the hot water storage under the pasteurization bassin. And this hot water storage is then feeding those pasteurization basins while it's mixed, of course, with cold water. So we will have water which is on a too high temperature, stored in an isolated vessel, and then mixed together with our with cold water to bring the exact amount of temperature to our pasteurization basins. And those basins then have an overflow function to the basins, so to the water volumes here. So those warm water will then also feed the water from the preheating and downcooling areas, and those overflow is continuing to the very sides of the pasteurizer. So all the heat which is applied in the middle is somehow coming to the sides and used recuperative to while the bottles are used as a heat exchanger to use as less energy as you want to, because tunnel pasteurizers are requiring just a lot of energy. This downcooling is not done fully to 10 degrees. It's done to 25 or 30 degrees in normal in modern tunnel pasteurizers, just to achieve some water savings. And all this is somehow a very complicated process, which it is just working when this is going dynamically, and the infeed of bottles is always the same, because I told you that the bottles are used as a heat exchanger for those for the water under them. And if we have for example, a problem at the filler, and we have a stop of the feed of bottles which is long enough to empty our buffer zone, and then the tunnel pasteurizer gets less bottles for a certain amount of time. All this concept is not working anymore because the amount of surface which the bottles are giving as a heat exchanger is of course less because there are less bottles in there. So those tunnel pasteurizers are, every tunnel pasteurizer is built and calculated very specifically to just this tunnel pasteurizer for all those mechanics to work. And if you have stops, or if you have a less input of bottles, you have to do something, just because normally for those calculations there are no gaps allowed. So how you regulate the temperature? As I said, the bath temperature is calculated according to the mathematical model, which is individual for each pasteurizer, which means that you just have to find out with experiments how long it takes for the very cold spot in your bottles, for example, to get at the pasteurization temperature. And this you have to adjust to how fast they are going through and how the temperatures in the different water volumes are. And in the end, when everything of this is calculated, you can say without looking how much pasteurizing units in your bottles are achieved. And the only really control variables are like how fast the bottles go through there normally, because you always, for terms of energy saving, you always want to stay at a certain temperature in your water volumes. So you differ the amount of pasteurization units by the speed the bottles are going through normally. Just foresee a few influencing factors on the pasteurization units. Of course, we have the duration of the heat treatment, which is the transport speed, but the container geometry is influencing this a lot, as you can probably imagine. If you have a bottle which is just way thinner, so the volume in there has more surface compared to a bottle which is thicker, where the volume has less surface where the water can be applied. So thicker bottles which have another ratio where the surface to volume ratio is that the surface is less for the same volume, of course have to go a little bit slower through tunnel pasteurizer than bottles which are higher and have a higher surface to volume. The headspace capacity is of course also a thing. So if you have a bottle type where it's sometimes with your filler not that easy to achieve the required amount of headspace for a pasteurizer, you probably have to go down with the pasteurization units to not apply an overpressure to your bottles that probably your containers can explode. Of course, the heat conductivity is something which you have to have in mind. The container has a specific heat conductivity, the liquid has a specific heat conductivity, can also differ through different beer styles a little bit, for example, but also what quality of glass do you have. Of course, this is very complicated, and normally you just try to be a little bit over everything to be safe, but those are all things which you have to have in mind. And what can you do if you have increases or decreases in output, for example? So if you want to increase the output of a tunnel pasteurizer, you have to you can do two things. You can go with the bottle slower, or you can increase the bath temperature to reach the necessary pasteurization units. So your tunnel pasteurizers can work at different bath temperatures, water bath temperatures. They will be the most effective at a certain one, but of course, if you have, for example, a Hefeweizen, which is always something very difficult because of the high carbonation of Hefeweizen. So normally you want to have flat pasteurization with this, but you can increase the bath temperature for this. When you have a decreased output, you can reduce the water bath temperature with fresh water, and this is what is happening when when in a filling lane it appears that that you have a decreased output of a filler, which can happen through a lot of things, like, for example, your bottle washing machine has a problem and the filler is working on half speed for, I don't know, half an hour when there's really a problem, and then your buffer zone's empty, and then you will have a decreased output of your tunnel pasteurizer, and those tunnel pasteurizers then reduce the bath temperature that they can still go the same speed with applying less pasteurization units in this time. There's also, of course, with those, a special program if they really have to stop. When a tunnel pasteurizer has to stop, you have the problem that the bottles in the pasteurization zone will get over pasteurized if you don't get them out. So there is a special cooling program then which just flushes those bottles with fresh water, which is kind of a little catastrophe in terms of energy consumption, because then you just like flush your hot water basins with cold water and you have to reheat them after. So this is something you really want to avoid. And for this, of course, filling lanes are also designed that you have big buffer zones before a tunnel pasteurizer to not let this happen. And as I also said, there can't really be gaps if you want to be energetically effective. So the infeed always has to be constant, and you try to achieve this also by going slower and then decreasing water bath temperatures, which is still better than having gaps, because when you have gaps, the bottles don't work as the heat exchanger as I described, and then you will have an energetic problem. Also, your other basins, your water bath, will not be as cooled down and as heated up as it is required for the mathematic model for your specific tunnel pasteurizer. And while those bottles go through a tunnel pasteurizer, we will have a convection flow through the bottles. So as long as we heat them up, we will have heating up of the liquid in the sides, so in the outer layers of the bottle. So that liquid will be lighter than the liquid in the middle, and it will start to flow up while it's pressuring the liquid, which is cooler, down. And when we then cool the bottle down, we of course have this, but the other way around. It's a little bit like in your fermentation tanks. Also, of course, this is happening somehow in the bottle due to that application of heat. And probably you also see here that at different bottle areas there will be different pasteurization units achieved. You won't have a constant pasteurization throughout a bottle. There will be a cold spot, which is, of course, it's very container dependent, but somehow here, normally there's a cold spot in your bottles. And also when you do some experiments, for example, you frequently put some trackers in your I've got the heating and cooling. Yeah. When you put some temperature trackers in your bottles, they will have to track the temperature at this point, because this is the coolest spot, and the coolest spot is this one where you really want to achieve those 60 degrees. So keep in mind that your bottles, when they reach the pasteurization area in the tunnel pasteurizer, the coldest spot has to have the pasteurization temperature at least. So everything else in your bottle is a little bit over pasteurized at this point, just to also kill the microorganisms at the cold spot. And of course, this heating speed depends on the container size. 330 milliliter bottles will heat up way faster than 500 milliliter bottles. And you will have different programs in the tunnel pasteurizer to achieve this, and not different tunnel pasteurizers, because those machines are probably the biggest ones in the filling lane, and you will not have two of them. When you want to control your pasteurization units, you will do this probably with one of those gadgets here, where you have a bottle in there with a tracking system which is tracking the temperature. You can also achieve this with putting trackers in there and then close the bottle. But you see a lot of those ones also. Just keep in mind that due to the very specific convection flow in your containers, that bottles also have to stand, because in some of those devices they don't have to for bringing them through. But this is not really simulating what is really happening with a convection flow in the tunnel pasteurizer. So you will have not the results you want to have. And then, of course, different containers, as you can see here, will have different different applications of heat. And but you will see this more or less all the time. So in the outer layers, you have this thin boundary layer which is flowing up. You will have in the middle the main core, where you will have a downflow of the heated up water, which is then coming to the middle, cooling down a little bit, and then sinking to the middle in comparison to the a little bit warmer liquid in the outer layer. And then in the down part of those containers, there will be a turbulent region from where the flows to the side, upflows to the side layers will rise from. And from those rising currents, which will then be in the side of your container. Yeah, the accuracy of those tunnel pasteurizers and also of your control is a little bit limited, because of course you want to design a tunnel pasteurizer as good as possible in terms of applying the heat at every spot at the same amount. But of course there will be differences. You will have different warm or cold zones even in your pasteurization zone. They will differ a little bit, but they will differ. And then of course you have your mistake of measurement. So your method of getting an overview of how your pasteurization units are has a mistake of 8 to 10%, and you have to keep this in mind. And also you will have to keep this in mind in terms of, okay, if you are on the very edge of the pasteurization units you're probably too low, because if you calculate this mistaken, you're way under what you need, and you will have to put this calculation mistake always on top to really be safe with your microorganisms in your liquid. And on the other hand, pasteurization units under 60 degrees are not recorded for beer, because there's this base of 60 degrees for the calculation of pasteurization units for beer. But of course, there will be some thermal inactivation happening before. You can also calculate this in. Modern tunnel pasteurizers do this in terms of energy consumption. But if you are calculating your raw pasteurization units and also those measurement devices, they will just say and record and also calculate PUs when in the cold spot of the container the 60 degrees are reached. Otherwise, they won't do that. So yeah, just to tell you again, yeah, those containers have to stand. They shouldn't lay, because when they lay down, there will be not the kind of pasteurization and the kind of flow you want to have. Just because we talked so much about, you can also see here a little bit of a temperature profile, which is in this case true for beers. So we have our pasteurization unit term here, and as you can see, the temperature in the bottle is rising, and just at the point where we reach the 60 degrees here, the pasteurization units are calculated. The calculation of this amount of heat treatment, you can include this. It's a little bit also dependent on whether you, of course, think, yeah, okay, we are safe because we have this treatment here before. Normally you say, okay, my calculated units start here. So there is an uptake of, oh no, sorry, sorry, this was a little bit confusing for you. I will delete this. So of course, what is right is that your pasteurization units are starting here, because here you reach the 60 degrees. I'm very sorry that I mistold you. And the pasteurization units are calculated until the point where you start to cool down, which makes, now this graphic makes a lot more sense. So after, in this cooling down process, your pasteurization units are not counted anymore. But as you can see here, you have a long time in the pasteurizer until you start calculating those pasteurization units. And also your heating up will be way slower than your cooling down. Probably some of you can tell me why this is, why we have to heat up slower than we are cooling down.
Is it to avoid cracks in the bottles?
Yeah, indirectly, yes. Yeah, true. So of course there can apply heat cracks, but there also cooling down can lead to cracks in bottles. Those cracks are mostly dependent on the heat differences, but the reason why we heat up slower than we cool down is that your beverage is carbonated, and as higher you get with the temperatures, as higher the saturation pressure in your for the carbon dioxide in your liquid is, given to the amount of carbon dioxide which is in the liquid. And it appears that when you go with higher with the temperatures, the saturation, the theoretical saturation pressure of what could be in the bottle, given the terms of physics which are behind that, is not achieved in the very moment, and it's achieved over time. So as longer you have a container heated at a certain temperature, as closer the pressure in the container will come to this saturation pressure. And this is not the only influence factor. Other influence factors are how fast are they heated up, and also for example, how much shaking is done. And this very slow upheating is due to that you want to keep the pressure in the bottle as low as possible before you reach and also while you have the pasteurization. So as smoother you do this, as less close to the saturation pressure of your liquid, the inner pressure of the bottle comes. This is why you do this. And when you cool it down, you of course just are lowering the saturation pressure. So in this case, you can go faster, and just have to be careful for what you said, that there can also appear cracks due to heat differences, and you have to take this in mind. But the saturation pressure is then not a problem anymore, because it will it will decrease when you decrease the temperature. All right. Yeah, this is basically what I was telling you before. So we will also have a little chart for that. So the inner pressure increases while heating up due to, of course, the expansion in a liquid is a little bit stronger in the glass, but not that much. The main pressure applications are due to the amount of carbon dioxide which is bound in the liquid, and will then of course also go to the gas phase. Yeah, but this is not really what I was telling you this. I'm really sorry. You of course will also have carbon dioxide losses. From the liquid to the airspace, but this effect is really small because the pressure itself in the container gets higher. The air in the headspace, of course, expands, and this is mostly one of the combined with the saturation pressure of the carbon dioxide is one of the reasons why we have a pressure uptake in the beverages. And while the beer is expanding, also additionally carbon dioxide goes into the headspace. And this is the reason why we have to have this minimum headspace of 3% for a 0.2 or 0.33 liter bottle, just because this headspace will then be filled with more carbon dioxide, and there will have to be some space for avoiding that pressure uptake. And yeah, as you can see here, this is what I was explaining. So there will be a point where the saturation pressure is not the pressure which is in the headspace, and there will be a point where the saturation, where those lanes are meeting, for example. So when you have a saturation pressure of for 3.5 grams carbon dioxide per liter, which is the yellow lane, there will be, in a 3% headspace bottle, you can have your beer at certain temperatures for a certain time without having that, and at a certain point this will just go straight up, and this is why you have to be very careful. This is why you also are doing this very slowly. The problems with tunnel pasteurizers is that even if you are very careful, you will have container breakages, because the filling process is stressing the containers, and there will be probably some cracks in there. And so you will have some medium going into your water bath. So you're slowly contaminating your tunnel pasteurizer, which requires, especially in the zones where the water is not warm enough to reduce the growth of microorganisms, require a lot of cleaning in between. And this container breakages mostly appear when you have little cracks in your bottles or when you have overfilled containers. Sometimes corrosion can be a problem due to the water you're using in your tunnel pasteurizer. Normally, newer pasteurizers don't have that problem, but older pasteurizers which are not from stainless steel can have this. Then you can have petrification, which means that you will have an excretion of water salts. When you have this petrification, there will be a higher heat demand and a danger of contamination, because you will have areas where will be surfaces created where microorganisms can be, and then with the breakages of containers, which will appear in your tunnel pasteurizer from time to time, even if you're very slow in heating up, you will feed those microorganisms, and then you can see sometimes a very big growth of microorganisms in your tunnel pasteurizer. And since your tunnel pasteurizer is open to both sides, it's also a source of contamination for your whole filling lane then. So you really have to be careful with that. Of course, also problems are production interruptions or product changes, which always require a stop in the tunnel pasteurizer in terms of production interruptions. Or sometimes if you have a product change and you're not fast enough, you will probably also have a gap, and we talked about this gap and how bad it is for your recuperative heat usage. So you have some problems with that. We will also compare a little bit the tunnel pasteurizer to the flash pasteurization technology, of course, what advantages and disadvantages you have with that. And just to give you a little bit of an overview about what a standard pasteurizer is using, is consuming of water and electric power of thermal energy, and what heat recovery rate can be achieved. And with a modern tunnel pasteurizer, you can achieve around 70%. That's possible. Your pasteurization units are gotten through an indirect measurement, which needs or requires a kind of pasteurization units count tolerance, that you just know you have a mistake of 10%. And you will have some beer losses, of course, due to breaking containers, which you also have to have in mind. Normally, the space requirement of a tunnel pasteurizer is 3 to 3.5 square meters per 1,000 containers per hour, depending on the throughput and, of course, the container diameter. So those are probably the most space requiring machines or machines in your filling lane. Also, of course, bottle washing machines are very big, but tunnel pasteurizers normally also require the same or even a bigger amount of space. We saw a little bit what how tunnel pasteurizers are working. I see some mentionings in the chat. Probably I will. Is the tunnel pasteurization of bottles different from that of cans? Yes, it is. You have to be way more careful. You can just not apply the same amount of heat with the same saturation, pressure, and carbon dioxide diluted in the tunnel pasteurizer for cans than for bottles. Cans, when they are seamed well and just then, are more or less sustainable until, or not sustainable, but so they have to be stable until like 6.2 bars. Bottles can have way more, especially when they're new. So when you go up to 10 bars in the bottle, it's normally not a problem if it's not an old bottle. So you are limited in what you can pasteurize in a can in a tunnel pasteurizer, which is dependent on the most of the time on the medium, which is in there, and the amount of carbon dioxide which is soluted in the medium. Do avoid breaking bottles? Fragezeichen. I'm not sure what you mean, but yeah, of course you want to avoid the breakage of bottles at all times. It will just happen sometimes. The modern filling lanes work with an astonishing amount of preciseness, but even then you will have some cracks in bottles which the empty bottle inspector did not see probably, which are not big enough to cause a bottle breakage while the pressure application while filling, but the pressure application during pasteurization will be higher, so you can have bottle breakages always in there. You can't avoid that by 100%, but to avoid that, you are heating up very slowly. You have to exactly know what medium with what carbon dioxide can stand is in your containers and how much the containers can stand. But this is still a problem which exists frequently in breweries, that sometimes just there's a new product, they don't really know how it's behaving, because the uptake in pressure in a tunnel pasteurizer up to probably close to the saturation pressure is also sometimes dependent on the medium. So carbon dioxide is bound to medias with sugar, for example, way better than to just a medium which is just water. And it's always happening when you have a new product. It's a common thing that then you have some breakages before you are really able to adjust. And sometimes it's just not possible, and you see, okay, my can seamer, for example, is just can seam just this good, and also my cans are just able to stand a certain type of pressure, and my tunnel pasteurizer is just not suited for pasteurizing this product in my cans. And a lot of breweries, in fact, especially big ones, have both. They have flash pasteurization and they also have a tunnel pasteurizer, and they use the flash pasteurization as often as they can, because this is way more energy effective. You consume way less energy, and just very very sensitive media, which probably cause problems when you can't flash pasteurize some other tunnel pasteurizer. And yes, you have a zip program for tunnel pasteurizers, and you should really make sure that this zip program is working well. It's just very, very important to do that. Probably I'm not sure whether I have a picture in this presentation about what can grow under a tunnel pasteurizer when you don't do that. But yeah, just imagine there is always some medium in terms of beer coming through your tunnel pasteurizer, which is contaminating that, and you really have to clean this after every filling cycle. This is very, very important. Okay, let's continue with the presentation. When we come to flash pasteurization, probably remember that this is happening before filling. So we pasteurize our product before it's in the bottle. And just for this and how those machines work, they require way less space than a tunnel pasteurizer. It's normally done right before filling. And just to give you a little overview how it's working. So we have beer in our beer lane, and it's heated to at least 71 to 74 degrees Celsius and held for 15 to 30, sometimes 60, depends on the medium, seconds, which then applies between 11 and 15 pasteurization units. Those flash pasteurization is happening through 2 or 3 stage plate heat exchangings. I will also come to that in a minute, how it's really working. But in fact, you are preheating your cold beer, which has to be pasteurized, with the pre-cooled or with a beer which is coming hot from your pasteurization steps. So you will try to leave the energy in the system as good as you can. And this is way more effective than when you have an open system as a tunnel pasteurizer with a lot of bottles in there. You just have beer and your heat exchangers. You can isolate this way better. And this is why the energy consumption of this is way lower, also due to, for example, that there are no containers to heat up. It's just the medium which has to be heated up. And the heat source which is solely used is hot water. So there will be a hot water tank for your for your flash pasteurizer, because due to this very short amount of time which the medium is in there and the high temperatures, and also we learned that that a temperature increase is very effective in raising the pasteurization units or lowering the pasteurization units when the temperature is decreased. You can't rely on a heat source which is changing. So what you have is a water tank which always has the same temperature, which is heated up by steam, but you don't use steam as a heater for the beer. You use water which you can set to a very specific temperature and to a very specific controllable flow. So the heat exchange is always the same to achieve a stability in terms of always the same pasteurization units, more or less, and not like having spikes to the up or to the down parts. And the adjustment of the flow rate, then when we say, okay, the hot water has always the same temperature and always the same flow rate while we exchange the heat with the beer, we adjust the flow rate of the beer. Through this flow rate, we adjust the PO value for the treatment. Flash pasteurization is, as I said, done before filling. So then filling should be aseptically, which modern filling lanes can do very good. And as older your filling lane gets, as less hygienic design you have, and probably your filler is just standing there and is not covered in a little, so modern fillers are covered in tiny houses. So the whole filling procedure is happening under other conditions than in the rest of the air of your product lane are. And you probably have to sterilize your bottles or cans. Beer is an easy medium to pasteurize and also to keep clean. So normally it's okay with a normal beer that you, for example, just have a proper cleaning in your bottle washer, and then you cover, for example, all your buffer zones before that and everything until you go to the filling lane with little roofs that nothing can come really from the top part, and then you should be okay. This is done a lot of times in breweries, but just know that if you probably have a malt beer or something, I would not require you to do a flash pasteurization and then fill just bottles, because this is a medium where the tiniest microorganisms which can't really grow in beer can grow in, because there's a lot of sugar, there's less alcohol in your beverage, and then this can probably be a problem. With beer, normally it is suitable to flash pasteurize. And the main parts of a flash pasteurizer, we will also have a picture in the next chart. But we have the heat transfer, which is basically divided into the recuperation zone, where we have this what I said, this from the heating lane beer coming, preheating the beer which has to be heated. Then we have the heating area and the cooling area, and we will have a booster pump before heating. This booster pump is also for adjusting the flow, of course, to a very specific level, but also to just increase the pressure in our system, because our saturation pressure of our liquid will be, of course, getting higher and higher as higher the temperatures go. And so we don't want, in this case, of course, this machine cannot explode like a bottle, but what can happen is that, and what we don't have to happen, is that carbon dioxide is just degassing from our liquid, and for this is then creating bubbles and surfaces where the heat is not applied to the liquid, for example, and then we can have an insufficient pasteurization. So we really always want to stay above saturation pressure with the flash pasteurization, and for this the booster pump is there. We also have a bypass for starting and ending, so that you can go in circular rounds until you reach the temperatures you want to have. And then we have our heat holder lane, which is when we go back to the last one, which is the heat holder lane is this. So you basically just have a long area where the beer is isolated and stays for a very exact amount of time at the certain temperature for achieving the pasteurization units you want to have. And we of course need to have a pressure reduction valve if we really really go over the pressure the system can hold. And the pasteurization units in a flash pasteurizer are just calculated because you know the exact temperature of your liquid, you know the exact time it was in the heat holder due to the flow rate, and for this you know the exact amount of pasteurization units which appeared in your liquid when you have a turbulent flow. Of course, when you have a laminar flow, you don't want to have that. So no, you don't want to have that. You can't have that. So also your beer has to be fast enough to be turbulent for really achieving that. And of course, you have a buffer tank before or also after for really always having a feed. So this is the basic construction of a flash of the heat transfer in a flash pasteurizer. So we see here we have a beer inlet at 1 degree Celsius, for example, and here happens this recuperation. So the beer is heated up by the beer which is coming from here through the heating area, and this beer which was in the heat holder is then giving its thermal energy to the beer which is going through the upheating for the pasteurization. This is basically why this is so effective in terms of energy consumption. Then we will have this heating up to the certain temperature we want to have, and this is happening by hot water. And then we have this heat holding area, which is it's of course it's just a picture, but which is then happening most of the time, and in terms of those little lanes here for having the beer at the certain temperature for a certain amount of time. And in the end, when the beer comes out here, you will have to cool it down to storing or filling temperature. So normally it's the filling temperature. So here you can also save energy when your filler is, for example, able to fill at 15 degrees and not at 1 degree Celsius or at 5 degrees Celsius. So also this cooling down in the end can save a lot of energy if you don't have to do this this heavily, and as better your filling system is, as higher the temperatures can be by filling, and this can also save a lot of energy, especially in a modern filling lane. And when we just to give you an overview how really those flash pasterizers are structured, and you can see here we have the hot water, which is the orange lane, which is heated up by steam to the certain temperature, and then also pumped circular for giving, well, we have this in the second one, for giving its energy to the liquid. So we always have this circular flow of our hot water, which is heated up by steam, always to the same temperature, which is then heating up our beer. And as you can also see here, we have this, we have our beer coming in from here. And this is this booster pump I was talking about right before the final upheating to the final pasteurization temperature. The heat holder is, of course, due to the flow rate holding beer for a certain time. And here at the number 2, we can see again this recuperative heat transfer from our heated product to preheat our beer before the final heating of flash pasteurization. Where's my mouse? Here it is. And here we got our final cooling in the end with our cooling water or cooling soil, depends on what you're using. The heat holding is another thing. So the thermal effect is usually determined purely on the basis of exposure time at a certain temperature in the heat holder. So the inlet and outlet of the heat holder also must be counted towards the hot holding time. So not only the area where your heat holder really is, but also the little few centimeters of when it goes to the heat holder. Everything after the heating up is counting as the lane for heat holding, and you have to have this in mind when you really want to calculate your pasteurizing units. Of course, the machines, so the constructors of the machines will give you the calculation for that, in terms of that your program will normally calculate your pasteurization units for this. And for an even temperature distribution, you have to have a turbulent flow in your heat holder. Are you familiar with the difference of a tubular and a laminar flow? Little bit. Okay, so just for example, I'm not sure whether I can really draw that, but when you have a laminar flow, let's say this is our beer lane, and the beer flows from here to there. Then as long as you have a laminar flow, which is always appearing when the liquid is not flowing fast enough, the speed of the flow will be the highest in the middle and be lower in the outer parts. And as narrower it comes to the outer parts of the beer of the beer pipe, as slower it gets, until a point where you have directly on the surface here, you don't have flow at all. So if you would have a laminar flow in your heat exchanger, you would have a very fast flow in the middle, so not that many pasteurization units for your medium in the middle, and way too much pasteurization units at the side of the transport. So what you want to achieve is that at a certain temperature, this laminar flow stops and the flow becomes turbulent, which means that it's doing basically a little bit like that. And this achieves a proper mixture of the liquid while it's flowing through, and this achieves then an even temperature distribution. You will still have parts of laminar flows in the very sides at the surface of the beer lane, but that's something you can't really avoid. And in the end, you want to achieve that turbulent flow to really achieve an even temperature distribution. No. Just have to delete this a little bit for my other points on that chart. Yeah, of course. So heat holders in the brewing industry are, of course, mostly insulated due to heat losses. Otherwise, you first wouldn't be really able to calculate your pasteurization units. You will have heat losses in your heat holder, and normally those are calculated as well when you want to calculate your pasteurization units. And the machine normally does it for you. The software normally does it for you. But of course, those are insulated to don't have this, but you will have those a little bit. And for example, for this specific flash pasteurizer, you will have a temperature difference of 1.8 Kelvin through the heat holding section. And you have to calculate this somehow due to integration of how much pasteurization units you will have in the end. But if you know that, you can calculate it, and normally you don't have to do this by yourself as a brewer. You can just rely on what the software gives you as the pasteurization unit content. And as I also said, this booster pump is also mainly for besides adjusting flow, it's for having your liquid over saturation pressure, and your saturation pressure is going up while you're heating up, and while you're holding, it's more or less stays at the same level, and then it's falling down again. And as you can see here, the beer in the flash pasteurizer is always hold above the saturation pressure of the beer. So we have this heating up, and before this heating up, here is this booster pump. So here we will have the highest pressure applied, and then we have the during the heat holding. Of course, we will have some losses in pressure due to the losses which always occur when you have a surface where the liquid is flowing, and then of course you will have a falling down in pressure when you have the cooling down of the beer. The liquid is contracting, well, not really contracting, but a little bit, and also the carbon dioxide is way more likely to stay in the liquid, so the saturation pressure is lowering. So also the lowering in your system appears, and you just have to have in mind you always want to have a difference, and the difference, the pressure in the beer always has to be higher than the saturation pressure of the liquid, given for the certain amount of carbon dioxide you have in there. The benefits of flash pasteurization are way lower investment and operating costs that you have at a tunnel pasteurizer, as we also had due to questions. You really have to clean tunnel pasteurizers very frequently, and the cleaning of a very big machine, which is an open system, which a lot of water baths, is way more complicated than cleaning a system which you can just clean by flooring, for example, caustic for the system. So you have way lower investment costs and operation costs. Also the energy consumption is way lower. It requires way less space. You can just basically place it sometimes next to your filler and don't have to have a lot of space in your filling lane, or you have it somewhere else and just then bring the beer to the filler. You normally are tighter in the pasteurization units you want to achieve. So there's less over pasteurization. The process is still conformed to pasteurization unit specifications, of course, and this type of continuous operation also, of course, minimizes your product losses, because you can't have container breakages where no containers. So and the pasteurizing effect, you can always verify that online. So you see at just a certain point when you have a problem, you know that there's a problem, because you have the flow rate, you have the temperature, and if something of this drops or changes, you know this immediately and you can react immediately. And in a tunnel pasteurizer, in the end, it's very hard to see, okay, which bottles are probably over pasteurized when you had a problem, which are under pasteurized. It's a way more complex system, and when mistakes happen, it's way more complex to really verify how big your pasteurizing effect was in comparison to a flash pasteurizer. The consumption data are also way lower. I will also compare those both systems, of course, in the end a little bit. So you want to have to try to compare this now. But you see, you have way less water and electrical and thermal energy consumption, and this thermal energy consumption is to the higher heat recovery rate. We remember tunnel pasteurizers can go up to 70%, and a good, really new flash pasteurizer can go way over 90% of heat recovery, which then leads to way lower energy costs. And you have lower beer losses because you don't have container breakages, you just have losses and probably blending parts when you have the system full of degassed water, and then you go in with beer, and those mixing areas probably you can't like recover them fully, but those losses are really low compared to a tunnel pasteurizer. Okay, so let's just have a little bit of an overview about hot filling. So basically, it's done through flash pasteurization. You heat beer to 68 to 70 degrees with a flash pasteurizer, and you just don't cool it, which, as you know, because our heat recovery on our flash pasteurizer is working by cooling down the beer with the beer which is coming in, you can't really recover that heat, so you lose that heat. But what you achieve is that you fill hot beer or warm beer in bottles, which is just happening if you really preheat the bottles to like 40 degrees. Otherwise, the temperature difference is just too much, and you will have too many bottle breakages. You have a very high danger of carbon dioxide release, danger of bottle bursting. As I said before, oxidation and aging processes happen way faster when you have a hotter environment, a warmer environment. So, of course, the bottles have to be evacuated often to avoid oxygen intake. The evacuation of bottles is always done in a normal filling system, so this won't really be a problem, but the other parts which I mentioned really are a problem in terms of filling beer. You also have to fill at high pressures, so 7 to 9 bars normally, because that's then the saturation pressure of your liquid at a certain temperature. And your filling pressure still has to be above the carbon dioxide saturation pressure of the beer, and you have to somehow prevent overfilling, which leads to, you can do this by a long-term pressure relief, which means probably your filling machine is running way slower than it would at cold temperatures, or your filling machine just gets gigantic because you really have to have when you have this filling diagram of a filling machine, then you have these little parts of the cake where I don't know, evacuation is happening and pressure application is happening. So here's probably evacuation, evacuation 2, then you apply the pressure, and then you fill. And then you have all this area here. Let's have this like this, and this like this. And then you have all this area here where the bottles just have to, like, you need to give them time for this pressure relief, because otherwise they just overform, and even then it's not that good controllable. And the energy consumption is just way higher. Hot filling is not really done with beer due to the fact I mentioned before. It's done with other products which are probably not that, which don't have carbon dioxide, for example. Then it's way easier. Where you really want to be very safe about the product. So baby food, for example, could be something which is filled for hot filling. But then you have also a lot of other things which come to that. Also, you have a full bottle inspection, which is initially coming from baby food, and now coming from the water industry also to the beer industry. So there are some filling lanes now which have full bottle inspectors. But yeah, hot filling is just requiring a lot of energy. Recooling is not really possible. So your heat through your flash pasteurization or from your flash pasteurization is completely lost. And this is something you really want to avoid in a brewery where you still have very high energy costs. The bottles has to be warmed, which also requires energy. And so even a tunnel pasteurizer is way better, especially when you have this heat recuperation in the tunnel pasteurizer working well. But you will have a higher thermal load compared to flash pasteurization. I think I didn't talk about the thermal load so much now, but I just said that when you have your beer at 60 degrees for half an hour, it's way worse for your flavor stability than having your beer at 72 degrees for 2 minutes. And so a tunnel pasteurizer always is influencing your flavor stability in a higher amount, also due to the effect that you will have a little bit of an oxygen intake while you are filling. Even when you have a very, very effective and new filling system, you will have a little bit of an oxygen intake. And with this heat application over the way longer time, you will have bigger effects on flavor stability. The flash pasteurizer is really using just a bit of the energy a tunnel pasteurizer is using, and you can almost achieve a complete heat recovery. And for this, flash pasteurization is very attractive, but you have to be very hygienic in all your other parts of your work. Otherwise, you can cause yourself like really problems in terms of contaminations while you are filling. So let's compare a little bit those two main methods, how you pasteurize in breweries. And the upsides of a tunnel pasteurizer are that you're including the packaging material, so you can't really recontaminate your beverage. It's the safe method. You just have to say that. And if you have a warm environment, for example, you're filling beer with a lot of sugar. India, for example, they really like to drink pretty sweet beers, and the environment there is just like that microorganisms explode. And I would really think about flash pasteurization in this country twice, especially when you want to fill sugar-containing beers. And I would really recommend a tunnel pasteurizer for that. But you have a higher thermal energy consumption. You have to heat up the container. You have a higher water consumption. And yeah, everything is in terms of this is worse. You will get a higher thermal load in your product, and you just have way higher investment costs, way higher costs in keeping your machine clean. It requires a lot of space. You somehow have to. So a tunnel pasteurizer is that heavy that you really have to think about the statics of your house where your filling lane is in, and probably it's in another floor. And it's not initially built for that. You have to find out whether the tunnel pasteurizer is not just breaking your ceiling on the level above, and then your pasteurization and your filling stops for a longer time. And in comparison, the flash pasteurization just has a very low thermal energy consumption. You have a lower thermal load to the product, so it's also better for your product. Investment weight and floor space are way lower, but you have the possibility of a recontamination. That's basically the difference between those two methods. And just for probably when you have a quality control which is not really familiar in how pasteurization works, inactivated microorganisms are still detected when you use a PCR. So when your quality control says, "Oh, but there's so much DNA in your beverage, didn't you pasteurize?" Well, yes, you did, but the microorganisms remain in there. Of course, they're just inactivated. So also, for example, those fast tests when you just test ATP, the ATP is also still in those microorganisms and will react with your testing kit. So those both are not really methods to see the effectiveness of your pasteurization. You really have to see whether there are microorganisms growing. So you really have to plate them. You have to see whether they are colony-forming units. And yeah, what can happen when we pasteurize? I also talked a lot of that now, but just to summarize it a little bit, we have an acceleration of the oxidation processes. We have just very small influences on the bitter units, so that's not that much. We have only very small effects on color and only at very high pH values. So normally our color due to a Maillard reaction is not really, through a Maillard reaction is not really rising. We have most of the time, if we have one, we have a positive effect on head retention. So longer pasteurization time results in a complete inactivation of proteases, and proteases can destroy your head retention when they are still in the liquid and just slowly breaking down the foam building proteins into smaller protein particles, which then don't form foam. So you will have a positive effect on that, which is nice. And you can adjust your turbidity. I would have to look at whether we have a chart to this, so I'll tell a little bit about that now. So the turbidity adjustment happens when you, for example, in Germany, the customers are now not really familiar anymore with the idea of drinking a Hefeweizen with a little load of really yeast inside there, because normally the turbidity of a Hefeweizen comes from the yeast, which stays in the bottle, also probably to bottle fermentation. And but now the customers think, oh, there's this thing in the ground of my bottle, and then it's like kind of cloudy when I put it in. I don't know what to do, and they don't know that you just have to shake it and put it into the glass. So what is done sometimes that the turbidity of the beer is not achieved by yeast cells, which are as big enough to just settle down in your bottle, and after you have the bottle in your fridge, after a while your Hefeweizen gets clean. So you adjust the turbidity of your wheat beer with heat by denaturating proteins so that they fall out of solution and they form a way finer turbidity, which is staying more or less where it is, so it will not settle down in the bottle. So you can also use pasteurization for that, but just at higher temperatures. So a tunnel pasteurizer will not fix your turbidity or create a turbidity in your beer. You really have to go to higher temperatures in your flash pasteurizer for also longer periods of heat holding, for example. The pasteurization aroma can occur, especially when you have a high oxygen intake in a small brewery, and then you have a flash pasteurizer. You also experience that. Then you will have a bread-like aroma in your beer, especially in browner beers, which always have the tendency, or in darker beers, which always have the tendency to taste a little bit like that. And this can just be very much enhanced by pasteurization. And if this is a bright beer, it's really not a flavor you want to have. It can also, like, because the oxidization is happening faster, the beer can taste oxidized, it can taste somehow cooked. Do you know why it can taste cooked? You're familiar with the dimethyl sulfide problem? So so what you basically want to evaporate in your while you're wort boiling, and also your maltster is somehow is influencing this on a way higher scale by killing and also evaporating DMS, dimethyl sulfide, which can taste like corn, which is not that favorable in beer. And just probably you know about the problem that you have those precursors in your beer, the DMS precursor, and this has to be broken up by heat, and then the DMS has to be evaporated. So the same thing which happens when you have a too long heat holding time and a whirlpool which doesn't have an evaporation part is happening, of course, in your bottles when you heat them up. And there is still some precursor in your beer remaining probably, and then it can also like taste like cooked vegetables sometimes. This can also happen, but it's not that often. So yeah, those are just some aromas which can appear. Normally, if you do this at the just high enough for inactivating your microorganisms and your oxygen intake is low enough, you don't experience this in an amount which is really a problem. But for those pasteurization flavors, most of the time there are carbonyl compounds and oxygen, the relevant parts. And the values of different carbonyls increase by pasteurization just because other parts of the beer react to those carbonyls. And as more oxygen you have in there, this process is enhanced. So the pasteurization is accelerating the effects of beer aging. And most of the increased carbonyl compounds are still below the threshold levels. So this is what I said. Normally your pasteurization is not causing that, but when you have high oxygen intake and probably a higher pasteurization, probably due to that you are not able to work that as hygienic as you want in your brewery, because you have a small brewery, grown naturally, a lot of things which are not really done in hygienic design. You have a higher initial germ count. You have to pasteurize in a way that is more than it's normally required, just to reduce that germ count. And then you don't have the modern filling, which is really getting out the oxygen of the bottles. So then you can experience those problems. Otherwise, in normal, in a modern filling and pasteurization process, this is not really an issue or should not be an issue. And yeah, let's talk a little bit probably about maltoxazine, which is the most common part of those flavors which can appear while pasteurization. It's causing this bread-like aroma, which is formed during the Maillard reaction while killing, and basically caused by those both amino acids, proline and cysteine. During fermentation, those products are transferred into sensory neutral compounds, but they can be reformed under heat influence, and this is what happens then in your pasteurization process. If you have a high load of those Maillard reaction products, it can happen. So the main product of this reforming is maltoxazine, and just to give you a little bit of an overview of how this can affect your the evaluation of your beer. Please keep in mind this is the sensory panel of the DLG. This is a German panel of tasting, where 1 is the lowest and 5 is the highest. And this is an overall sensory evaluation. So in this case, they don't try to like see a specific or try to taste a specific compound. They just evaluate whether the beer is fresh or not. And when you look at the pasteurization temperature, a freshly pasteurized beer is not really differing from a not pasteurized beer directly after pasteurization. So this aging process is enhanced, but didn't occur in a way that you can taste it at this specific moment, which is then turning around fastly after 8 weeks, for example. And as you can see here, when you give the same amount of pasteurization units, especially when you have an amount which is a little bit higher, you see that higher pasteurization temperatures, which then lead to a lowered pasteurization time for that certain PU values, cause better flavor stability in terms of aging than longer pasteurization at lower temperatures. This is basically what we see here. So pasteurization at 60 degrees for 80 pasteurization units. I'm sorry that it's PE, that's the German thing. Will lead to a less good tasting product, or it's here, than, for example, when you pasteurize it at 72 degrees, where the amount of time where the beer has to be heated is just longer. Also, probably 2-enonenal, which is the referred to the cardboard flavor in beer. When you look at that in fresh pasteurized beer, this is behaving a little bit differently. But in the end, if you see the aging process, you see that this is highly tempered. It's way more pasteurization unit dependent than it is temperature dependent, especially when you have high pasteurization units. So in terms of the 2-enonenal after 4 weeks, you really want to have kind of a middle class of pasteurization units to not overgo this. But in the end, you really try to stay as low as possible with your pasteurization units. When you want to flash pasteurize top fermenting beers, which are also turbid, which I have to say before that, you see that the fresh character decreases when you have this flash pasteurization. Also, the fruity character decreases because also some parts which form the fruity character are just reacting to other molecules, and then they probably go under the flavor threshold. Typically, in a top fermenting wheat beer, this typical flavor is less recognizable after flash pasteurization because you reduce the amount of esters and higher alcohols, and as you probably also know, the esters are the main part which cause the very specific taste of a wheat beer. And you have to probably also, because the yeast is still in there, you have to use high pasteurization units. But this doesn't lead to an autolysis flavor, which is good. So the cells are dead, but they don't really break open in an amount that causes an autolysis flavor, which you really don't want to have. And also, you can detect an inactivation of yeast cells at 15 pasteurizing units beers, just not as completely as you have when you go to higher values. So for top fermenting wheat beer, I would really recommend higher pasteurization units than 50 pasteurization units. You want to have, as we saw, between 100 and 120. So we will not really have in those top fermenting beers reduced flavor stability, which is good, and also like is comparable a little bit to the charts we saw before, that flash pasteurization high temperatures has a lesser effect on flavor stability. Both decrease more or less in the same freshness, whether you pasteurize or not. Sometimes pasteurized wheat beers can have a slight unpleasant bad taste, but this is also dependent on how your pasteurization is, how intense your pasteurization is, and also on the medium. So sometimes it happens, sometimes not. It's not really foreseeable. But the aged taste is statistically on a lower level. And which I was talking before, so I also got a little bit of information about that. If you want to have a foam stabilization by flash pasteurization, you really have to go up with your pasteurization units and also at higher temperatures because you have to inactivate those proteases. So you can't really do this in a tunnel pasteurizer. Even if you would go to that high temperatures, the movement of liquid is too small, and there will not be a complete deactivation of proteases in the tunnel pasteurizer. And even this does not have a very big influence on the formation of an aging taste. So if you have problems with your foam stability, probably going like avoiding that with flash pasteurization could be something you can do. And as you can see here, foam stability is always somehow achieved when you flash pasteurize. So if you compare a not flash pasteurized wheat beer to flash pasteurizations at different pasteurization units, it's always increasing your foam stability just because always some proteases are killed. So it's really good for your foam stability to flash pasteurize, just to point this out. But this is of course an example for wheat beers, and if with another medium, with another beer, with another composition of proteins in your liquid, this can also vary. But for this example, this is true in this case. So now we come a little bit to cold pasteurization, which is basically, like, by definition, it's not really pasteurization. It's basically what I want to talk about with you now is sterile filtration a little bit. Are there some questions before about the themes we have talked now? So basically tunnel and flash pasteurization. Nice. Then we will continue. And just also here a little bit overview. Cold pasteurization, when you hear this word, is mostly meant as sterile filtration, and you can achieve this by a sheet filter, by a membrane filter, or by DE filtration. And I'm not sure whether you had the theme filtration, so I give you a little bit of an overview of how different kinds of filtration work. But just it is an alternative to flash pasteurization or a tunnel pasteurizer, and you can separate, of course, yeast and beer spoiling bacteria out of your medium. If you really can achieve that, you just have to have to have a proper pre-filtration. So you can't just filter your beer sterile in the first step; it will just block your filter. But if you do this correctly, you can also reliably remove the beer spoiling bacteria, and then face the same problems as you have with a flash pasteurizer, that you then have to fill your product, and your containers can contaminate your product again while during the filling process, or your filler can contaminate your product again. So same problems as with a flash pasteurizer, and you don't really have an impact on foam taste, color, or smell. Well, this is just true for the sole sterile filtration. Of course, the filtration itself has an impact on foam taste, sometimes also color. So, of course, your foam stability can get worse when you filter your beer. Just this last step of sterile filtration is not really affecting the remaining foam stability you have in your filtered beer. This is what I wanted to say. Just to give you a little overview about what kind of filtration is holding back which amounts of particles in which size. So as you can see here, you really have to do at least microfiltration at a very sharp level to really get all the bacteria out. If you want to filtrate until you get viruses out, for example, you have to go into the other filtration segment. And normally this particle filtration, as I said, is done before sterile filtration, just to remove all the bigger particles from the liquid, because the filter sheets for sterile filtration are very small, so the holes in there are very small, and they can get easily blocked by bigger particles, and then your whole filtration doesn't work anymore. So the working pore size for a microfiltration, which really removes all the bacteria you want, is has to be somehow between 0.1 and 0.2 micrometers, just to really get everything out which you want to get out. And the retention mechanisms of different filtrations are just brought you here to have a little bit of a pre-understanding probably about what we're talking. So you have surface retention, which is basically sealing, which means that the particles just can't get through your pores because of their size. So the pores are smaller than your particles, very easy, and you will have this accumulation of particles at your sieve, which is after a certain time also blocking your sieve. And then you have this depth filtration, which means that the particles are able to enter the pores, and the pores vary in size due to the depth of the filter sheet. And at a certain point, the particles will get stuck. And when they are stuck, they also they also reduce the amount of surface where other particles can get through. So also through a depth filtration. During a depth filtration, your filtration will get sharper and sharper as longer as it takes. And then we have this part of absorptive retention, which is often occurring also during a depth filtration, dependent on the material you're using, which means that there is an electrostatic attraction of the wall of the filter sheet to the particles which are filtered. So the particles are not stuck due to size, but they're stuck due to probably a chemical group which is comparable to a chemical group of your filter sheet, and then is absorbed there for that reason. And so when we look at cellulose filter sheets, we of course have a surface retention for bigger particles, but they mainly work through depth filtration and absorptive filtration, while a DE filtration is a solely surface and depth filtration. So you don't really have adsorptive effects of the filter material. What you have is adsorptive effects of the yeast, which is stuck in the filter material. So you always experience some kind of adsorption, but not in the filtration material itself. And then you have this, then you have, of course, membrane filtration, which is also somewhat state of the art in a lot of breweries nowadays. And it's mainly a surface retention method, which is working with a cross flow that you don't block your filtration surface too fast. And but it is also working a little bit with depth retention, and dependent on the material can work as an adsorptive filtration as well. Just to give you a little bit of an overview where your sterile filtration is placed, it's placed here after all your other filtration steps. So when you have this very like big like, this is a little bit too much because you have a DE filtration and then you have a sheet filtration as well. Normally you probably either have a sheet filter and a very good centrifuge. You can also have that. You don't really have to have everything which is in here. But when you have a DE filtration and a PVPP filtration, you will probably have a trap filter after that. And you can then, if you had a proper filtration and you have just very small particles in your beer, you can then sterile filter. This is basically what I wanted to show you here. Yeah, this is just, I just wanted to say, don't sterile filter your unfiltered beer. It will not work because your sterile filter will just be blocked in a very short time. Just for giving you a little bit of an overview about probably how you can do a sheet filtration, how those things are built off. It's just a little overview because that's not really the topic. But you will use layers of cellulose, fibrous silicose, and halides, and you have a large adsorbing surface which can absorb some bacteria, and you will have in those sheet filtrations, you will have mainly an adsorptive but also depth retention. And those pores are organic. When you have cellulose pores, they are very sensitive to pressure changes, which is not good, because when you have a really pressure change and you have a pressure spike, for example, then those pores can experience a widening which is not going back, and then your sterile filtration is letting some microorganisms through, and you don't really want to have that. So this is a little bit, can be a problem with those filtrations because those pressure changes can lead to changes in pore size. For the absorptive effect, you have to have really slow flow rates. So when you want to filter big amount of beer sterile with a sheet filter, you need a very big filter, just because the flow rates have to be very slow for your absorptive effect. And capillaries are blocked due to this adsorptive and also depth filtration, which can also sometimes, because your filtration will get sharper and sharper over time, and it can lead to the removal of colloids, some bitter substances. Yeah, you have to just count with that probably your beer will taste a little bit differently after your sheet filtration, especially when you're filtering with cellulose, for example. And you really have to filtrate very sharp before, otherwise you can just block those sheets. Your membrane filtration is always done with a synthetic polymer layer. Sometimes ceramics are, I think, also a thing. It is mostly solely surface retention with a defined pore size, which cannot change. So pressure changes are not a problem of that. And just to avoid the blocking of your filter surface, those membrane filter system are ran with a cross flow. Of course, I will not go into detail with that because that's not really the topic. Just to give you a little bit overview. The nominal pore size gives an indication of the deposit rate because, of course, the pores can vary a little bit. It's very insensitive to pressure changes, as I said, and those filter candles you don't have to exchange often because you can just clean them and then recycle them for next filling. And normally this is done through well, you have to replace your filter cartridges in a while. You don't really have to have a buffer tank. And the good thing about membrane filtration, where I wanted to come now, is that you have a lot of filter cartridges in one cluster, and then you have several clusters. And what you basically do is, when one cluster is full and blocked, you change to the other cluster, and in this time you regenerate the used clusters. So membrane filtration can normally just be very dynamical to a quasi-stationary process, because you can recover the one part which is not filtering while the other part is filtered. Just to give you a little overview, because sometimes you hear the word cold pasteurization, and by that means it's sterile filtration. So yeah, we are in the very end of this presentation. If there are questions which you have now, just feel free to tell me now. Otherwise, also you can mail me if you have some questions which were not I was not able to answer now, or probably which just come later. You also got this presentation for having a little bit for kind of having a look later. Also, due to that, the presentation is, I know a lot of charts are full of text. This is not nice representing, but it's nice for rereading, because then you have more information on the chart. So yeah, thank you very much. If there are questions, please tell me now. We have 5 minutes left for that. And yeah, I hope you enjoyed this presentation.
Thanks very much.
Thank you.
Thank you.
So we have one thing in the chat. Oh, where's the chat? Okay, thank you. Nice. I have there's the questions. Just thank you. So yeah, thank you very much for your attention. And yeah, I hope you enjoyed this. And yeah, probably we'll see each other later somehow, because the brewing industry is a place where you know each other after a while. So yes, thanks again for your attention, and have a great rest of the week.
Thanks.
Bye bye.